In the last sections of chapter 9, we will continue looking at the addition reactions to carbonyl compounds. To start our discussion here, however, we will look at the addition of enolates to carbonyl compound. First of all, let us define the enolate. So enolates are generated from the acid-base reaction of carbonyl compounds with an alpha hydrogen. You may recall that alpha is the first letter of the Greek alphabet. So here is our point of reference, the carbonyl. The first carbon next to the carbonyl is called the alpha carbon. And of course, as expected, the hydrogens that are bonded to the alpha carbon are called alpha hydrogens. As you saw from the chapter in acid-base chemistry, these hydrogens here are acidic. So in the presence of a base such as potassium hydroxide, one hydrogen is abstracted to give you a conjugate base, which is resonance stabilized, and this base is called an enolate. As you can imagine, here's the ene, and of course the olate is the salt. But these two structures here are in fact the resonance structures of the enolate, which is generated by the abstraction of the hydrogen, a alpha hydrogen from a carbonyl compound, in this case an aldehyde. So let us look at possibilities. So here we have an enolate which is generated in the presence of a base. It's in equilibrium, which suggests that we have both the enolate and the aldehyde present in solution, because it's an equilibrium reaction. The enolate, of course, as you can see here, is nucleophilic. And by the way, I should point out here that the nucleophilic end of the enolate is the carbon and not the oxygen. So the nucleophile here will attack the electrophilic carbon of the aldehyde. So it will form a new bond, as you can see here, and of course in the presence of water, a proton adds to the product. So once again, let's review this. So we have here an aldehyde which has acidic hydrogen based on the alpha hydrogen. In the presence of a base, we generate here a resonance stable enolate. Notice the term, enolate. The enolate is nucleophilic, as you can see here. This is an equilibrium reaction here. So we have aldehyde in the presence of the enolate. A nucleophile will add to the electrophilic carbon of the carbonyl to form a product. This type reaction is known as an aldol reaction. Why aldol? Because we have an aldehyde and we have an alcohol. Here's the aldehyde and an alcohol. So it's called an aldol reaction. Again, aldol reactions are very important reactions in organic chemistry because we're starting out here with a very simple molecule and we have created here a molecule that is much larger. So you should be able to look at an aldol product. Let me clear the board a bit and give you a better perspective. Okay, so here we have, let's get the pen again. So here we have an aldol product. You should be able to examine this aldol product very carefully and determine what are the reactant molecules or the enolate and aldehyde that make up this aldol product. So you can see for this lecture it will require a lot of critical and analytical thinking and observation. So let's go on. Here's another example. This time it's acetophenone. Here's the carbonyl carbon. Here is the alpha hydrogen, alpha carbon, and here are the alpha hydrogens. Notice this carbon here does not have a hydrogen. There are 4 bonds to that carbon already. There's only one set of alpha hydrogen, and it's right here. In the presence of a base, 1 hydrogen will be abstracted to form the enolate. In the presence of more starting material, acetophenone, we have an aldol adduct. Notice it's still called an aldol reaction even though this is a ketone. Okay, so this is an aldol reaction where we have an enolate serving as a nucleophile to react with the electropositive end of the carbonyl compound to form an aldol product. So again, you should be able to look at this aldol product and determine what are the 2 reactant molecules. In this case, what is the enolate and what is the carbonyl compound that reacts to make this product. Let's look at this reaction. Very interesting one, because here we have acetophenone, same as we had up here. 1 set of alpha hydrogen, none here of course. So the enolate that's generated is here. So let us say you introduce benzaldehyde, this molecule here. Notice this molecule here does not have alpha hydrogens. This hydrogen here is not an alpha hydrogen because it is not bonded to a alpha carbon. So therefore this carbon here, which is partially positive, this nucleophile can now react with this carbon, and of course now we have a new product, and this product is called a crossed aldol product because this reaction is called a crossed aldol reaction or a crossed aldol condensation. So again, you should be able to look at this molecule here and determine what are the reactant molecules. In other words, what is the enolate? Here's the enolate right here because of this alpha carbon. And what is the aldehyde or carbonyl compound that's used to make this product? So you'll have to do a lot of observation and look at these molecules carefully. In fact, you may want to pause the video here and just look at the product molecule and try to figure out if you can come up with the reactant molecules. Let's look here at the addition of enolates to carbonyl compounds. In this case, the carbonyl compound is an alpha beta unsaturated. So here we have a term, alpha beta unsaturated. Here's an alpha beta unsaturated carbonyl. So here's the carbonyl right here. This is the alpha carbon, and this of course is the beta carbon. The alpha beta carbon has a double bond, in this case an unsaturation. So that is why this molecule here is described as an alpha beta unsaturated carbonyl. Let's look at the resonance structure. You can draw the resonance structure putting a negative charge on the oxygen by moving these electrons, as shown with these arrows here, onto the oxygen. In that case, the oxygen acquires a formal negative charge, and the beta carbon acquires a formal positive charge. Bottom line is, in an alpha beta unsaturated carbonyl, this carbon here is partially positive. The beta carbon is partially positive. So let's see if we can apply that concept. So here we have a ketone. It has an alpha carbon here and an alpha carbon here, but those two alpha carbons are equivalent. Each alpha carbon has two alpha hydrogens, so therefore in the presence of a base we can abstract one of these hydrogens to create a enolate. So here's the enolate that's generated from cyclohexanone. As we said earlier, this carbon here is the nucleophilic end of the enolate. So when the electrons move back in, it will bond to the beta carbon of the alpha beta unsaturated carbonyl compound. The new bond that's formed is right here. Notice what we have here is an enol, enol, and as we know from previous chemistry, it quickly tautomerizes through a keto-enol tautomerization to give the more stable product, the ketone. So here is the product of the addition of an enolate to an alpha beta unsaturated carbonyl compound. This reaction is also known as a Michael addition. In some books you'll see it as a Michael addition or a 1,4 addition. Why 1,4? Because we have 4 atoms here counting from the beta carbon to the oxygen. So this reaction is called a Michael addition or an addition to an alpha beta unsaturated carbonyl. Look at the product carefully and see if you can determine the component reactants. Here is the ketone, which gives the carbonyl, the enolate, and here is the portion that came from the alpha beta unsaturated carbonyl. Lots of observations here and lots of analysis. So here's where organic chemistry is really utilizing the skills and helping you develop the skills of observation and critical thinking. Let us look at the product that we had before. This is the product. So, as you can see, here is an alpha carbon. Here is an alpha carbon. Here's an alpha carbon. And here is another alpha carbon. So we have quite a few alpha carbons in the product that's generated from the addition of an enolate to an alpha beta unsaturated carbonyl. Let us look at the abstraction of a proton from this alpha carbon using a base. This enolate is generated, and this enolate can react with this carbonyl here because this carbon is partially positive, an aldol condensation. If that happens, it forms a ring. So now we have a ring that's formed where this bond here is the new bond. So here we have the aldol product where this is the alcohol and the carbonyl. One may say that isn't it possible for this enolate to react with this carbonyl? Yes, it is. But the challenge is that it creates a four-membered ring that's not stable. The most stable system, as we have seen in chemistry, is the six-membered ring as we have shown here. So this is the most likely product, or the major product of this reactant in the presence of a base undergoing an intramolecular aldol reaction. This type of reaction has a name. It was discovered by Robinson, and so it's known as the Robinson annulation reaction. Annulation here means ring forming. So it's a ring forming reaction discovered by Robinson. So another term is an intramolecular ring forming aldol reaction, or you can just say the Robinson annulation reaction. Again, look at the product carefully and see if you can determine how that six-membered ring was formed. Let's look at the application of this. So before we actually do that, however, this is the aldol adduct, as we just indicated. In the presence of heat and not elevated temperature that's too high, it readily occurs. Elimination of water is possible to form here another alpha beta unsaturated ketone. So this becomes the product of your Robinson annulation, an unsaturated ketone as the product, where this double bond here is coming from the dehydration or the elimination of water from this molecule. As you know from resonance structure, whenever you have resonance structures where you can delocalize electrons across a number of atoms, that's a stable situation. That is why this product here is more stable than this product. So this readily happens. So the overall reaction of the Robinson annulation is the ketone in the presence of a base gives you the enolate. The enolate reacts with the alpha beta unsaturated carbonyl, and that in the presence of more base gives you the Robinson annulation, and here's the product. Again, I use different colors here, but make sure that you can determine the component molecules here in the presence of a base to give you this as the product. As you can see from that product, which has two 6-membered rings that are joined, they form the basis for a lot of organic compounds in chemistry, particularly in the pharmaceutical industry. So this presents a very effective method of making compounds looking like this. Let us see if we can apply this chemistry. So here is a molecule. So that's our target molecule. And the question now is, can you determine what are the two reactant molecules that are needed in the presence of a base, such as potassium hydroxide, to make this molecule? It requires a lot of analysis before you can come up with an answer. First, here is our carbonyl. Here is the alpha carbon. Here is the beta carbon to this carbonyl. So more than likely, this could have been the alpha beta unsaturated carbonyl right here. So the double bond would have to be here. By the way, I just noticed a misspelling here. So the double bond would have to be right here. Notice again, the other component would be right here. Here's the carbonyl. Here's the alpha carbon of the other molecule. And in the presence of a base, that would be the enolate. So the two component molecules would have to be right here and right here. Let's see how we can put this all together. So if you had this as your ketone, and here is the carbonyl, here's the alpha carbon, which has two hydrogen. Notice this hydrogen is not a alpha hydrogen because it is not bonded to a carbon that is an alpha carbon. Here is our alpha beta unsaturated carbonyl. So this as an enolate will react here, and here's that new bond. And of course, what we have here is the addition to the alpha beta to form here the new product. That's called the Michael addition. Let us look at a more complicated application. So here, using the Michael reaction and the Robinson annulation, can you provide the synthetic route to make this molecule? So this requires a lot more analysis and the applications of the reactions that we have covered so far. First of all, the observation is, here is the important end of this molecule, or a good starting point. The carbonyl and the alpha beta unsaturation. So more than likely our analysis will start right there. Let us see how we can carry out the observation and the various analyses. So here's that molecule again. So the strategy is we can make this double bond by the elimination of water. So if we had this, using again retrosynthesis thinking, or the reverse thinking, means working backwards. If we had this molecule here, we can make this double bond and hence this target molecule. The question now is, how do we make that molecule? Let us keep going back. So if we had this molecule here, you can see here that if you had this as the alpha carbon, which has alpha hydrogen, in the presence of a base, it can react with this carbonyl to make this bond right here. So next we want to make this carbon-carbon bond by an aldol reaction. That's also called the Robinson or the ring forming reaction. Let's see if we can go further back. So to make this bond here, we can see that if we had here this as the enolate, or we can make the enolate from this ketone, cyclohexanone, in the presence of a base, in the presence of this alpha beta unsaturated carbonyl, this will add right here because that is the positive end of that unsaturated ketone to make this bond. So that's the strategy that we'll use to make molecules of this type. So the overall reaction is starting off with this ketone, cyclohexanone, in the presence of a base, and this alpha beta unsaturated carbonyl. Using a Michael addition, we can make that bond. In the presence of more base, because we have a alpha carbon here that has alpha hydrogens, in the presence of a carbonyl compound, we have a ring forming reaction, aldol reaction, or the Robinson reaction, to give us here this product here, which is the aldol product, and the removal of water here gives us the final product. So that's the analysis that you'll have to make in carrying out these synthesis. More than likely you'll be asked, given this molecule here, what are the reactant molecules in the presence of a base that's needed to make this as our target molecule? Let us turn our attention now to the reaction of the addition reaction involving amines to carbonyl compounds. So we start off here by looking at a carbonyl compound, in this case butanone, in the presence of an acidic medium such as a proton. These electrons can bond to the proton to form this intermediate. Notice that if you drew a resonance structure, this carbon here is positive. In the presence of an amine that is nucleophilic, it can react here to form this bond right here. Loss of a proton gives us the addition product. So addition product here is the addition of H and amine to the carbonyl. That's the addition product. Notice the equilibrium reactions. So in the presence of more acid, it's possible to protonate here the oxygen, and as shown here, it's a good leaving group, so it leaves as water to give us this resonance stabilized cation, which has here a nitrogen and a pair of electrons, and here's the resonance stabilized species. You can readily see that loss of this proton here gives you the final product, which is neutral, and this is called the imine based on this feature here. So again, the addition of an amine to a carbonyl gives this as the initial addition product, but that's not the isolated product. The product that's actually isolated results from the loss of water to give us the imine as the product. Let's see the importance of this type reaction. Starting again with butanone, reacting this with hydrazine, here's the amine portion of this molecule, so it forms the imine here. This type molecule is called a hydrazone. Same type reaction here. This is called hydroxylamine. Here is the imine portion, but now it's bonded to an OH. Here's the imine portion. This type molecule, because of the OH, is called an oxime. And the same type reaction here to give an imine here. And of course, this is called a phenylhydrazone. Just different names for the imine reaction. These reactions are very important intermediates, again, in the pharmaceutical industry, because they are intermediates in making much larger molecules. Let us turn our attention to the addition reaction involving imines. So the reactant molecule, the product that we just made, the imines, can they react further? Yes, they can, because as you can see, it is a covalent bond. It is a polarized covalent bond where this carbon here is partial positive and this nitrogen now is partial negative. So it will react with an electrophile in a regiospecific manner to add the electrophile to this nitrogen because of the nucleophilicity here, or the partial negative. Since if there is a nucleophile present in a second step, it will add to this carbon here to give you this as the final product, looking like this. Let us look at the other possibility. In a basic medium, where we have lots of nucleophile looking like this could be like your OH negative. The reaction takes place again in a regiospecific manner, where this nucleophile will react at this carbon or add to that carbon to give us this intermediate. In a second step, if an electrophile were present, it reacts to give this as the final product. The same type final product, but two different steps or two different ways of getting to that final product, depending of course on the medium, if it's a basic medium or an acidic medium. Let us look at the acid catalyzed addition of water to an imine. So here is our imine functionality. It's an acid catalyzed. That means we have an excess of protons. And here is our nucleophile. Of course, as you know, it has an unshaded pair of electrons. So it will add to this carbon as shown here, and the proton will add to this nitrogen here. So that's our addition product, initial addition product. So if you're asked to write the product of this reaction, this would be it. I should point out, as I pointed out earlier, in the presence of more acid, because it's an equilibrium reaction, it's possible to protonate here, and this water can add to this nitrogen here to form this, and this becomes your addition product. So this is the mechanism. This is the mechanism here, where these electrons here add to the proton, or the proton adds to these electrons to form this intermediate. Water adds to this to form this, and of course this proton leaves here to form that as the product, initial product. So that's the mechanism. Let's look at this. As I mentioned, there are equilibrium reactions, so it's possible to go further. So in the presence of more acid, okay, the protonation can occur here or here. If it occurs over here on the nitrogen, this intermediate is formed. As you can imagine, this group here can take its electrons to form this as a leaving group, leaving behind here this intermediate. A loss of this proton gives us a neutral product here, which of course is a ketone, a cyclohexanone. So as you can see, we can go here from the initial addition of water to an imine to form this product, and it can go on to form the cyclohexanone or the ketone. The next slide gives a summary of that. So here we have the imine in the presence of an acid reacting with water can give us the carbonyl compound, and of course the protonated amine as a product. Why protonated? Because the acid here is in excess. So if you had this imine and water as a reactant in the presence of an acid, and you were asked to predict the product here, this is the product based on the elimination of the amine in the presence of an acid. Let us look here at the reaction of nitriles, or the addition reaction to nitriles. Here again, you may recall this is the functional group of a nitrile. Carbon, nitrogen, triple bond. As you can see here, even though it's a triple bond, it is a polarized triple bond. This carbon is partially positive, and this nitrogen is partially negative. So as you can imagine, in an excess of electrophiles, this is a regiospecific reaction. The electrophile will add to this nitrogen to generate that intermediate. This nucleophile will add to this carbon to generate that as your product. You will recall this is an imine. And as you know, the imine in the presence of an electrophile will add further to give us here the amine as our product. So let us see if this is possible in the presence of a basic medium. So if we have an excess of nucleophiles, so no protons are present here in the first step, we have a large excess of nucleophiles such as OH negative. So if this reaction were to take place in KOH, for example, KOH would add here first, regiospecific, to the positive carbon as shown here, and in a second step, step 2, the electrophile would add to this nitrogen here as shown to give us the imine. So again, this is the overall mechanism of this reaction here as shown. So the first step is the nucleophile reacting with the nitrile to form the imine reacting with an excess of nucleophile to form the amine. Let us apply that. So here we have an acidic medium and water. So in the first step, as you can imagine, these electrons will bond to the proton to form this intermediate. This electron, or one of these pairs of electrons here, can bond to this carbon as shown here. As you can imagine, this is an intermediate because of the charge. Loss of the proton will give us that as a product. It's possible for protonation to occur to give another intermediate, and of course electrons moving in give us an amide as the product. So this could be a product, but as you can imagine, it prefers to have a carbon-oxygen double bond compared to a carbon-nitrogen double bond. We have seen that analogy when we looked at the keto-enol tautomerization. The carbonyl bond is preferred over the carbon-carbon double bond. Here the carbonyl double bond is preferred over the carbon-nitrogen double bond. So this is the final product of the reaction of a nitrile with water in the presence of an acid. That's why we say it's an acid catalyzed reaction. I should point out, however, that if the reaction is heated, the final product is actually a carboxylic acid. So here we have an amide, and without going into much details, which we'll cover in a later chapter, there's a substitution of the NH2 for the OH here to get a carboxylic acid. So take-home lesson is, if you have an amide in the presence of an acid and water and heat, the final product that's isolated is a carboxylic acid, where the NH2 is replaced by an OH. So the overall reaction here, or the overall reaction scheme, is if you have a nitrile in the presence of an acid and heat, not as much heat, a low temperature, you get the amide. In the presence of an acid and water and elevated temperature, much higher temperature this time, your product here is the carboxylic acid. So again, if you're asked, what is the final product of reacting this nitrile with an acid in the presence of water and, most important, heat here, the final product is a carboxylic acid. Okay, let us look here before we conclude on the application of addition reactions. So let us say you're asked to use this as a starting material and you wanted to end up with this as your product. So the question would be, show how to carry out the following transformation. Here's what we're asking. The question mark is asking, what are the reaction steps and what are the reagents that you would use to convert this reactant molecule into this product. Before you start writing any reactions, however, as a good chemist, a good scientist, you need to do the observations. The observations here are, number one, there are 2 additional carbons in the product that are not in the reactant. 2 additional carbons. So we have to introduce 2 carbons. So one of the reactant molecules must contain two carbons. The other aspect here is that the reactant molecule has a carbonyl. The product molecule does not, or the target molecule does not. We know from experience we can convert a carbonyl to a carbon-carbon bond by using a yelid. That's called the Wittig reaction. So it's coming together here. Another observation is that we have here a water molecule, an OH, that's in the product, that's not in the reactant. So we'll have to introduce OH. Typically, we introduce OH molecule, OH group by hydration, adding water. And of course, to add water, addition, we need a double bond here. So if we had a double bond here, we can do a Wittig reaction. So now that all of this information is in our head, or we have come up with this observation, our job now becomes how to communicate all of that to us, the grader, that you know how to carry out that transformation. That's a challenging job, but it's a job that you can do if you apply the information carefully. So here's what we would expect. So here again is the question with the question mark. Doing the retro-analysis, starting from target molecule and working backwards. If we had this molecule here, we can do an anti-Markovnikov hydration to get this product. Notice it's an anti-Markovnikov hydration addition reaction, a reaction that you did from a couple of chapters ago. So that's called retro-analysis. Continuing with the retro-analysis, if you had this molecule, what molecule will it take to make it? So if you had this molecule here, you can make this molecule using a Wittig reaction, where this is the yelid. Again, we're combining all the applications and the reactions that we've looked at earlier. This is the yelid, and this type reaction is called the Wittig reaction. So this is a summary of our retro-analysis. So here are the steps. Step number 1, you would react this molecule here with the yelid in a Wittig reaction to get an initial product. You'll react that initial product with borane followed by oxidation to get the anti-Markovnikov addition to the double bond, which would give you the target molecule. So what's expected if you should get a synthesis question? I should not say if, when you get a synthesis question, because all the quizzes and exams from here on will have at least one synthesis question. What's expected is either one of these as your answer. You could write it out step by step, or you could just include on the arrow the various steps. Notice step 1, 2, and 3, and the reactant molecules. Make sure you include the reactant molecules so that we as graders, we can see that you understand this material and you are applying this material to solving a very important synthesis question. I think this is the last slide. So again, continue to study hard. This is a very involved chapter. It involves a lot of thinking, a lot of analysis. That's why organic chemistry is one of those courses that helps to develop your problem-solving skills. So pay a lot of attention, put a lot of time into thinking how to solve these problems, because it will help in developing your problem-solving skills, which is important in your development as a scientist. So we'll have a quiz on Thursday, which will cover the rest of this chapter 9, and I'll post another video on chapter 10 towards the end of the week. So once again, continue studying hard. Take your time to make sure you understand this material. Take your time to make sure you can apply this material. Take your time to make sure that you can communicate your understanding of this material. Okay? Bye.